Hi everyone, welcome to the Machine Learning Security Evasion Competition 2020. My name is Zoltán Balázs and I'm the head of Vulnerability Research Lab at Kujo AI. I had some offensive research in the past. For example, you might have heard about the Zombie Browser Toolkit, the Hardware Firewall Bypass Tool, the Malware Analysis Sandbox Tester Tool, or you might have heard that I played with some crappy IoT devices, or I invented the idea of encrypted exploit delivery via Diffie-Hellman key exchanges. Besides these offensive researches, I'm the co-organizer of the Hackerschule meetup here in Hungary, and I'm the program committee member of the Hacktivity conference. This is a joint research together with Dr. Hiram Anderson. He's an architect at the Azure Trustworthy Machine Learning at Microsoft, and he's the co-founder and co-chair at Chemlis organization. His background is from signal processing and machine learning, but he's also very good when it comes to information security. His main relevant research is that he created some code regarding reinforcement learning-based AV evasion, and he's also the co-creator of the Amber datasets. Machine learning is used in an awful lot of different ways in our life. For example, researchers can use machine learning to classify objects. And for example, when the machine learning model looks at a photo, it can decide whether there's a bus or an animal on this object. There was some interesting research done in the past to trick these machine learning classifiers. On the left side, you can see a normal bus, and on the right side, for the human eye, you can see the same bus, but because there was an added layer to this photo, if you try to classify the photo on the right, it will classify this as an ostrich. But we are in information security right now, so we are interested in malicious software detection. There were multiple research in the past how you can bypass machine learning based malware detection. For example, last year, some researchers found that if you extract strings from a game file and just dumbly append these strings to a known malicious executable, you can bypass the machine learning detection. I also did some research in the past, and 4 years ago, you could even bypass some machine learning models just by packing the file with a known packer like UPX. Luckily, this has changed recently, so you cannot use this trick anymore. Me and Hiram thought that there's a nice potential here to create a competition. So we created the website evademalwareml.io, and what you had to do is basically download 50 working malware samples and download 3 machine learning models with its weights, modify the malware samples to evade the detection by these machine learning models, submit those to our website, and if you achieve the highest scores, you could win this nice NVIDIA GPU. The outcome of this competition was pretty interesting. Around 70 people registered for the competition, and at least 11 were able to bypass at least one machine learning model. At the end of August, William Flashman submitted his latest samples and scored the maximum score you can have in the competition. I highly recommend everyone to go and check out his excellent blog post about how he was able to do this. You can also find other interesting write-ups. For example, you can check out Jakub Debski's or Fabricio Ceschi's research and how they were able to bypass the machine learning models. For example, it might be interesting to see whether you can bypass detection by using a packer. Packers were mostly used in the past to bypass AV-based AV signature detection. But turned out that because in this competition we are using binaries and some of these samples are already packed, adding another layer of packer on top of it might break the functionality of the sample itself. Another interesting solution was to add new sections to the PE executable. And for example, you can extract resources from known files like Microsoft files and add these resources to the malicious sample. Turned out, again, this can be very effective to evade the models in our competition, but unfortunately it broke some malware because some malware samples had packers or self-checks, and just by adding a new section to the sample broke the functionality. Fun fact, just by adding a simple empty section to sample, you can even bypass some antivirus engines. I believe this is because of performance reasons, because the AV engine can quickly check how many sections are in a malware and only use those signatures on the sample which check the section size. So this can be a nice trick for your AV evasion. Last but not least, the winning strategy was to append some extra data to the executable. This technique is also called an overlay. And even though this is very dumb and plain, turned out this was the winning strategy after all. And Williams' solution was to brute force the ML models and found the pattern which evades all machine learning models. And again, fun fact, by significantly changing the size of a sample, for example, just by adding a lot of overlay to it, you might be able to bypass some AV engines. Again, I believe this is because of performance reasons. For example, here you can see one malware sample we are using in the competition. And if you are adding some overlay text to the end of the sample, you can see how the visual representation of the file changes. Some key takeaways from last year's competition turned out that the malconf and non-nec malconf machine learning models are a bit too academic and they are not very effective when it comes to practical malware detection. The LEAF project, which you can use to modify binaries, is awesome. And it's not that shocking, but dealing with malware is tricky because the IOCs they can produce can change over time, which makes it hard for us to detect whether this is the same sample or not. And there was also this added challenge that some packed and protected samples are hard to deal with. I also checked some of these samples with the SSD hash, and turned out that those samples which had either these repeating sections or some repeating overlaid data, they create repeating patterns in the SSD hash itself. And one interesting fact is that from now on, you can basically check the SSD hash of a sample, and if you see repeating patterns in it, it might be suspicious because in an average benign binary sample, there are no repeating patterns. There is no reason to do that. So this could be some way suspicious that, so for example, someone tries to evade a machine learning model with this technique. This year, we created a new Defender challenge on the top of the Attacker challenge, where you had to create your own machine learning model and submit it to the competition via Docker format. And in the Attacker challenge, you had to evade these previously submitted machine learning models, but now this was a black box attack compared to last year, where the challengers had white box access to these machine learning models. This year, our sponsors and partners are Microsoft, Gujo AI, VMware, and MRGF with us, but the main organizer people remained the same in the competition. And one reason why it makes sense to participate in our competition is that you can win Azure credits for your machine learning research plans. In the defensive track, we received 2 submissions which passed the minimum requirements. And you can see when you submit your samples that there are 3 models right now: the Ember model, the Need for Speed model, and a random string model, DOMOB. These are the malware families we have used in the Attacker offensive track, which ends at the 18th of September. At the time of this recording, this competition has not finished yet, so we don't know the results. The flowchart of the Attacker challenge is that you go to the mlsec.io website, register there, review the terms and services and accept it, download the 50 provided malware samples. You somehow modify your samples and hope that it will evade all 3 machine learning models. We also hope that you check your malware functionality in a Windows 10 sandbox. And new this year, we have an API to submit your samples or query the results. If you don't like the web-based UI, then you can use this API now. And whenever you are satisfied with your samples, just create a zip file and upload it to our website. You can get up to 3 points for each sample based on how many machine learning models you evaded. And the highest score wins. But this year, we are also counting the number of total API queries, which is counted whenever you check a sample with a machine learning model. And in order to claim your prize, your solution must be published on a blog post. As it was the case last year, please check that your file names remain the same in the zip file, otherwise we have no way to identify which sample is which. And besides the tricks last year, we have also some additional tips and tricks you can use to manipulate the binaries. For example, you can add or remove signatures, change the section names or properties, modify the import or export tables, create a TLS callback, change the PA header, maybe fix or change checksum, add, modify, or remove the version information, create a new entry point, or change some code or data which does not affect the behavior of the sample. Still, it's not allowed to use droppers or self-extracting arrays, and multiple registration is against the rules and will result in immediate disqualification. Feel free to join our Slack channel. And last year and this year, if you are interested how we have created this challenge, It's all based on Python Flask admin, and we are using Cloudflare, Nginx, and GUnicorn for scalability and performance reasons. And we are running Python backend scripts, and we are using the VMRay sandbox to check whether the malware sample behaves the same as it was originally. As mentioned, we have an API this year. For example, if you want to submit your sample to all machine learning models and get an immediate feedback on it, you can see the API endpoint on the point 1. Or if you just want to submit your sample to one specific ML model, you can do that as well. On the point 3, you can see the API endpoint to get the results. Or if you already are satisfied with the results and want to upload your zip file with all the samples, you can do this with the API as well. Or you can query the specific zip status or query all samples or specific samples based on these API endpoints. But let me show you how this really looks like in practice. So you visit our website mlsec.io. You definitely should check out the rules because you have to be familiar with everything what's written here. We also recommend you to check out our GitHub page. For example, for the attacker section, Hiram already uploaded some interesting files which you will be able to see later. Now, if I go and log in to the website, here, as you can see, you can download the malware samples for this competition. And if I check what's inside this compressed zip file, you can see it's 50 samples with sequential names. And now your task is to change these files in a way that hopefully it will bypass the machine learning detection, but still the sample will remain functional. Now let's go and upload our file, and let me show this to you. It's important that in the zip files the file names remain the same and you don't use any directories, for example. So let's download this new zip file and let's see what will happen. I paused the recording for a little bit, but now, as you can see, the samples has been started in the analyze process, and here you can see all the different information from my test upload. As you can see, even though these executables were valid new executables for the competition, I was not able to bypass any of these machine learning algorithms, mainly because I did not intend to do so. But as you can see, now the whole sample processing started. It's also interesting to check out your user management site and change your nickname to something better, because by default it's randomly generated. And it's also important to have a look at the total API queries, because this counts into your total ranking, and every time a sample of yours is submitted to a single machine learning model, this counter is incremented by 1. And now if I check out the scores section, you can see that someone already has the best scores when it comes to bypassing the machine learning models, because we have the free machine learning model and 50 samples, so that's a total of 150 scores. But this contestant used 741 total API queries for his solution. So maybe we don't know, maybe someone else will be able to achieve the same score with less number of total API queries. Basically, that is all what I wanted to share with you. You can also remove some of your samples if it was not able to bypass anything. You can also filter these columns if you are interested, or you can also export all of data from this table to a CSV file if you want to process it for yourself. So that's all. Thank you. This is all I wanted to share with you guys today, but please stay, because here comes Hiram Anderson, who will show you an example solution which could have been used to win the competition.
My name is Hiram Anderson, and I'm delighted to present virtually at Hacktivity. I'm going to be presenting the Machine Learning Evasion code walkthrough. This tool was included in the sample solution to the attacker challenge in the Machine Learning Security Evasion competition. You can download and play with this code by visiting mlsec.io and navigating to the attacker challenge GitHub repo. Our example solution was designed with the following things in mind. Number one, the models to be attacked were submitted by contestants in the Defender challenge that concluded previously. 2 models from the previous round qualified to be included in the attacker challenge. In addition, we have hosted our own model to be attacked that is based on the Ember dataset. The models to be attacked report hard labels for submissions provided to them. That is, they do not provide a score between 0 and 1, but just a 0 for benign and 1 for malicious. Finally, we considered the leaderboard criteria while designing our solution. The first criterion considers the number of model evasions. With 3 models and 50 malware samples, the maximum score is 150 points. A tiebreaker would be decided by the efficiency in which the models were evaded. So we count the number of model queries. Thus, contestants are incentivized not only to be evasive, but also to do it efficiently. Contestants were able to choose any strategy that they like. To demonstrate one strategy, we released this example code on our competition's GitHub site. The code uses discrete optimization over functionality preserving file modifications using a package called HyperOpt, which ironically is often used for tuning machine learning models. You can learn more about the details from the code and documentation on the website. However, the broader strategy may be of general interest. It consists of employing an algorithm in part A to get the bulk of the malware to be evasive while remaining functional, followed by any additional manual steps in part B to fix any few remaining samples. We use the example code in our strategy in part A, in which we break our algorithmic attack into 2 phases: an offline attack against a known defender model for which we have code and weights, and an online attack. The hope is that many of the samples that were discovered in the offline attack will cross-evade the hosted online models without having used any additional queries against the API. You may visit mlsec.io to download this code. However, please be warned that when you run this demo code, you will write functional malware to disk. So please do so only using a Linux VM. To begin, we initialize the attack by analyzing a collection of benign files. The init subcommand extracts elements of the benign files that will be injected later into the malware. To launch our offline attack, we first run a local copy of the Ember model in the top window. Then in the bottom window, we'll use the run subcommand of our attack script, passing in malware samples that were downloaded by contestants. The tool will write successful evasion attempts to pass1/success and failed attempts to pass1/failure. Also included in each directory are history files that would allow us to resume our optimization of failed attempts. In a second pass, we begin with only the pass1 failures and iterate on the optimization, again storing successes and failures to a folder of our choice. Having now collected candidates that evade the Ember model, we use those candidates as seeds for an online attack, which now counts against our API query usage. The online attack is enabled with a simple -- online flag. After several iterations, we can now gather the successfully evasive variants and create a zip file to be uploaded to the website. Since there is a chance that the file modifications have broken some of the files, contestants have been encouraged to run the samples in a Windows 10 sandbox to validate functionality before uploading to the competition website. As a final note, since the hosted models may learn from the queries issued by contestants, there is a possibility that an evasive variant discovered by a contestant at the beginning of the competition may no longer be evasive to a model by the end of the competition because the model has changed its state. We're recording these talks prior to knowing the winners of the Attacker Challenge. I would like to preemptively congratulate those who have won our grand and first prizes respectively. In order to receive those prizes, the contestants must publish or blog about their solutions. I look forward to learning about the winning competition strategies and would like to thank our sponsors and partners for making this competition a reality.